So, let's go.
Right now, a spacecraft is somewhere between Mars and Jupiter, flying toward an ocean that contains more water than every ocean on Earth combined. And nobody knows if something is alive in it. There are 10 missions happening this decade that are going to end the biggest fights in astronomy. Not eventually. This decade. Some launched last year. One is already sending back data. One is politically on life support. And China might beat everyone to the most important discovery in human history. Here's what's coming. Number 1. SPHEREx. In March 2025, NASA launched a telescope shaped like a megaphone into orbit. It doesn't look at one thing. It looks at everything. Every 6 months, it scans the entire sky. Not in one color, but in 102. Colors you can't see. Colors that carry information about what the universe was doing before anything existed. Here's what it's hunting. In the first billionth of a trillionth of a trillionth of a second after the Big Bang, the universe expanded by a factor of a trillion trillion. In less time than it takes light to cross a single proton. That event, inflation, left a fingerprint, a subtle pattern baked into how 450 million galaxies are arranged across space right now. SPHEREx is reading that fingerprint. The number that matters is called FNL. If it's anything other than 0, the simplest model of inflation is wrong. If it's wrong, we have basically no idea what caused the universe to exist in the first place. That's a Nobel Prize sitting in the data. And the data is already coming in. Oh, and in August 2025, an interstellar object flew through our solar system. Scientists pointed SPHEREx at it and found water ice. The first time we've ever confirmed water traveling between the stars, in the first year of its mission. It's going to be a busy decade. Number 2, the Vera C. Rubin Observatory. The sky isn't static. You know that intellectually. Stars explode. Black holes devour stars in a burst of light that briefly outshines entire galaxies. Asteroids drift past. Stars flicker. The universe is restless and violent and constantly shifting, and for most of human history, we just couldn't watch fast enough to see it. On June 23, 2025, that changed. The Rubin Observatory in Chile has a camera the size of a small car, weighing as much as half an African elephant. 3,200 megapixels. One single exposure covers the same area of sky as 40 full moons. And it runs every night for 10 years, building the most complete time-lapse of the universe ever attempted. Every explosion, every flicker, every dark wandering object, cataloged and time-stamped. Here's the number that should stop you. The original dark energy discovery in 1998, the one that won the Nobel Prize, the one that told us the universe's expansion is accelerating, was built on roughly 50 exploding stars. Rubin will find more than that in its first few months. It's named after the astronomer who proved dark matter exists back in the 1970s. The observatory bearing her name might finally tell us what dark matter actually is. But to really settle that question, you need to bring in the Europeans. Number 3, Euclid. Everything you've ever seen, touched, built, or broken is made of normal matter. Atoms, protons, electrons, all of chemistry, all of physics, all of you. And that stuff, all of it, is 5% of the universe. The other 95% is something we can't see, can't touch, and have no complete theory for. Dark matter, dark energy, most of everything. And we barely understand it. Euclid launched in July 2023, and it's currently mapping it. Not directly. You can't photograph darkness. But dark matter bends light. When light from a distant galaxy passes through a clump of dark matter, it distorts. Euclid maps those distortions across a third of the entire sky, building a three-dimensional picture of where all the invisible mass is hiding. In March 2025, the first dataset arrived: 26 million galaxies. Over 500 perfect rings of light, places where a massive invisible lens is bending a background galaxy into a halo. Dark matter filaments stretching between galaxy clusters, exactly where the models said they'd be. And over 100 free-floating objects, too big to be planets, too small to be stars, just drifting alone through space. Things Euclid wasn't even built to find. The real results drop in October 2026. Buried in that data is an answer to a question that's been quietly tearing astronomy apart for years. Two groups of scientists measured how fast the universe is expanding. Using completely different methods on completely different objects, they got completely different answers. Both groups did everything right, and that's the problem. Number 4. The Nancy Grace Roman Space Telescope. The disagreement has a name: the Hubble tension. The early universe says the expansion rate is 67.4. The local universe says 73. A 9% gap. At cosmic scales, that gap means the two camps disagree on the age of the universe by about 1 billion years. Every instrument sent to settle it has made the problem worse. When the James Webb Space Telescope launched, astronomers quietly hoped it would find an error, some contamination, some artifact that explained the discrepancy. Instead, it confirmed the measurements. The gap is real. It's now sitting at almost 5 standard deviations of statistical significance. In physics, 5 is the threshold where you stop calling it an anomaly and start calling it a discovery. In September 2026, Roman launches. Same mirror size as Hubble, but the field of view is 100 times larger, and the survey speed is 1,000 times faster. It's named after NASA's first chief of astronomy, the woman who, in the 1960s, built the committee that eventually produced Hubble. She died in 2018 without knowing if her second telescope would ever fly. Roman is going to map 1 billion galaxies and pin down dark energy's behavior with enough precision to answer one very specific, very uncomfortable question. Is dark energy getting stronger over time? Because there are hints from a major survey in 2024 that it might be. If Roman confirms those hints, the universe doesn't end in a slow fade. It ends in something considerably worse. 20,000 terabytes of data, over 5 years, all immediately public. Anyone with an internet connection gets to look. The cosmology questions either end or explode in the next few years. But those are questions about the universe as a structure. There's a different question entirely. Is it empty? Number 5. Europa Clipper. Jupiter has a moon. Europa. About the size of Earth's moon, wrapped in a shell of ice. Beneath that ice is a global saltwater ocean that has existed for billions of years, sitting in darkness, pressing against a rocky seafloor. It contains 3 times more water than every ocean on Earth combined. NASA launched a spacecraft to it in October 2024. Right now, it's crossing the solar system. It swings past Earth in December 2026 to pick up speed, then arrives at Jupiter in April 2030 and begins running laps around Europa. 49 of them, over 4 years, dipping as low as 25 kilometers from the surface, roughly where commercial planes cruise. The mission's official goal, word for word, is not to detect life. It's to assess whether Europa could support it. This is a scouting mission, not a discovery mission. That distinction matters. But here's the thing. In 2012, Hubble spotted what looked like water vapor plumes erupting from Europa's south pole, ocean water venting into space. Follow-up observations were mixed. Nobody is certain those plumes exist. One of the instruments on Clipper is a particle collector. If the plumes are real, it will fly directly through them. If that water carries amino acids or a specific molecular chirality, the left-handed twist that biology imposes on chemistry, the scientist reading that data is going to know what it means before they finish the sentence. Standing on Europa would end you in about 10 hours. Jupiter's radiation environment delivers a lethal dose that fast. The ocean floor is under over 1,000 atmospheres of pressure. Complete darkness. Completely sealed off from sunlight for billions of years. Those are almost exactly the conditions around hydrothermal vents at the bottom of Earth's deepest oceans, which are full of life. Whether life can survive in Europa's ocean is one question. How life would have started anywhere is a completely different one. Number 6. Dragonfly. Saturn has a moon called Titan. It has a thicker atmosphere than Earth. Lakes, rivers, and rain. Sand dunes stretching across the horizon. It's larger than the planet Mercury. Everything about that description sounds almost familiar. None of it is. The rain is liquid methane. The rivers and lakes are liquid natural gas. The dunes aren't sand. They're grains of frozen organic chemistry, billions of years of atmospheric reactions slowly settling onto the ground. The sky is a permanent orange haze. Thick, you'd never see a star through it. In July 2028, NASA is launching a car-sized, nuclear-powered rotorcraft to fly across it. Titan's atmosphere is 4 times denser than Earth's, and its gravity is 1/7 as strong. For a flying vehicle, that combination is almost generous. Dragonfly will hop between dozens of landing sites, sampling the chemistry at each one, traveling farther across a planetary surface than any rover in history. The target is an impact crater called SPHEREx, 90 kilometers wide. When the asteroid hit, it melted the icy bedrock. For tens of thousands of years, there was a pool of liquid water, mixed with the organic chemistry sitting on the surface, sealed under an ice lid. A prebiotic soup, simmering in the cold. The origin of life on Earth is genuinely unsolved. We know amino acids can form from simple chemistry. A scientist proved that in a lab in 1952. What we don't know is how you get from amino acids to the first living cell. That jump happened on Earth over timescales we can't replicate in an experiment. Titan has been running that same experiment on a planetary scale for 4 billion years. One of Dragonfly's instruments hunts for chirality, the molecular handedness that biology imposes on chemistry. If it finds that signature at SPHEREx, then the chemistry that leads to life might not need a warm ocean or a sunny coastline. It might just need time. 4 billion years is a lot of time. Number 7. Mars sample return. Right now, a NASA rover is driving across the floor of a crater on Mars that was a lake 3.5 billion years ago. Water flowed in. Sediment settled. Chemistry happened. If life ever existed on Mars, this is where it would have been. Perseverance has been collecting samples since 2021. 33 of 43 tubes are filled. Each one is a sealed titanium cylinder, the size of a cigar, packed with rock from an ancient lake bed. They're sitting on the Martian surface right now, waiting. The plan was to retrieve them, launch them off the planet, and return them to Earth by the early 2030s. Lab instruments here can run tests 10,000 times more sensitive than anything that fits on a spacecraft. We would know, with actual certainty, whether those rocks contain evidence of ancient life. Then the cost estimate arrived, between $8 and $11 billion. In January 2026, the U.S. House of Representatives effectively canceled the program. China is launching its own Mars sample return mission in 2028. Simpler mission, single landing site, not the curated collection Perseverance spent years building. But it reaches Earth by 2031, years ahead of any American option. Here's why this matters beyond the politics. In 1976, NASA landers ran an experiment on Mars that produced results consistent with living microbes in the soil. Scientists spent decades arguing about what those results actually meant, because the data was ambiguous, and nobody could go back to check. That argument is still alive today, 50 years later. The samples in those tubes would end it. or start a completely better argument, one with actual physical evidence. And when the samples come back, whenever that is, they have to be opened inside a biosafety level 4 containment facility. The highest category, the kind used for Ebola and smallpox. That facility doesn't exist yet. Number 8, the Square Kilometre Array. The universe had a childhood we've never seen. Not because there's no record. There is. But for several 100 million years after the Big Bang, there were no stars. Just hydrogen gas, slowly cooling in the dark. Then, the first stars formed, and their light ripped the electrons off all that hydrogen, and the universe went from opaque to transparent in a cosmic instant. That moment, the first light, the end of the Dark Ages, is called the epoch of Ryanization, and we have almost no direct observations of it. The Square Kilometre Array is being built to change that. 131,000 antennas in the Australian desert, 197 dishes spread across South Africa and 8 other African countries. They function as a single instrument, the largest radio telescope ever constructed. In June 2025, with less than 1% of the final array installed, a test image found 85 galaxies in a patch of sky equal to 100 full moons in 7 hours. The completed array will find 600,000 in the same patch. The photons it will detect from the epoch of reionization have been traveling for longer than the Earth has existed. But here's what makes this strange. A few years ago, scientists scanning data from an earlier, smaller version of the instrument found something nobody had a category for. Giant rings of radio emission, up to 1 million light years across. Invisible to every other telescope on Earth. Just vast, silent circles of radio light hanging in the sky. They named them odd radio circles. 5 years later, nobody knows what they are. The full array will find hundreds of them. Every time a new telescope opens its eyes, the universe has something unexpected waiting. Number 9, EnVision. Venus is almost exactly the same size as Earth. It formed at roughly the same distance from the Sun, at roughly the same time, from the same stuff. If you were building a twin planet from scratch, Venus is what you'd get. The surface temperature is 465 degrees Celsius, hot enough to melt lead, zinc, and tin simultaneously. The atmospheric pressure is 92 times Earth's, equivalent to being 900 meters underwater. The clouds are sulfuric acid. The last probe to land there was a Soviet spacecraft in 1985. It survived about 2 hours before the heat destroyed it. Something catastrophic happened to Venus, and the unsettling part isn't the catastrophe itself. It's that we barely understand what caused it. The entire surface was geologically reset, all at once, somewhere between 500 and 700 million years ago. Every crater older than that is gone. 2 theories. Either Venus's lithosphere periodically peels away from the interior and resurfaces the whole planet in one violent overturn, or it's been slowly burying itself with volcanism for so long that the old craters simply can't be found. In 2031, ESA's EnVision spacecraft launches to find out which one is true, carrying radar 3 times sharper than the last mission 30 years ago, plus spectrometers to hunt volcanic gas and a sounder that can see beneath the crust. But underneath the geology is a quieter horror. Some climate models suggest Venus had liquid water oceans as recently as 700 million years ago. It may have been habitable for longer than life has existed on Earth. Something tipped it over. A runaway greenhouse effect. Atmospheric collapse. The oceans evaporating into space. And the mechanism that started the cascade is not fully understood. Venus isn't just a dead planet. It's a case study in how an Earth-like world becomes uninhabitable, and we've spent almost no time studying it. Number 10, LISA. Every mission in this video uses light. Infrared, radio, visible, ultraviolet, Different wavelengths, same fundamental principle. Photons, electromagnetic radiation. Humanity has been reading the universe through light for the entire history of astronomy. We've gotten extraordinarily good at it. LISA doesn't use light. In 2035, ESA and NASA will launch 3 identical spacecraft into orbit around the Sun, trailing Earth. They'll position themselves into an equilateral triangle, each side 2.5 million kilometers, more than 6 times the Earth-Moon distance. Between each pair of spacecraft, a laser fires continuously back and forth, and the instruments listen with almost unimaginable precision for the moment the distance between them changes. The strongest signals LISA is built to catch will shift those arms by roughly 1 meter over 2.5 million kilometers. The instrument measures changes 1,000 times smaller than that. What generates a signal like that? 2 supermassive black holes, each containing billions of times the mass of the Sun, spiraling into each other over millions of years and finally colliding. The energy released in gravitational waves in those final seconds exceeds everything the Sun will emit as light across its entire 10 billion year lifetime, released in moments. LISA expects to catch dozens of these events per year, and every one of those events is also a new, completely independent way to measure how fast the universe is expanding. No distance ladder. No assumptions about the early universe. Just space-time itself, carrying the answer. Every other mission in this video is asking a question. LISA is growing a new sense. And when you develop a new sense, you never know in advance what you're going to perceive. That's always been the part that matters. These aren't missions being planned for some future generation. Most of them are already flying. The data is already arriving. Somewhere in the next few years, a scientist is going to look at a result on a screen and understand something no human being has ever understood before. We just built the instruments to make that possible.